Welcome, ladies and gentlemen, to some Integrated 2 math. In today's episode, we will be dealing with solving quadratics using a different technique known as completing the square. Now, in the case of the first two examples here, if we were given a quadratic that looks like this, set equal to 0, what we would do up until this point, if we with the skills we have, is we would just factor each quadratic, set it equal to 0, which is pretty easy. This one I can kind of go for it. I don't have to use any kind of diamond or anything like that because the leading coefficient is 1. I'll go and split my x's accordingly, and then I've got to figure out two numbers that are going to multiply to 7. I'm going to throw down a 7 here and a 1 here. Since my signs are double positive, I'll go ahead and throw down both positives here. And with x plus 7 times x plus 1 being equal to 0, I can then set my individual pieces equal to 0. This technique that I'm doing right now is what's known as the zero product property. And it's called that because I've got a product happening and it equals 0, so I set the individual pieces equal to 0. So from here, it's pretty simple. I would just solve for x, so x would be negative 7, and then x would be equal to negative 1. And any type of quadratic that's factorable will fall under the guise of the zero product property if we're going to solve for that quadratic. So this one here being a difference of two squares, I'll go and just split him up again into two separate bubbles. And this would be x minus 12 and x plus 12. Again, I can just kind of go for it. These are pretty easy factors. Nothing really too crazy here. X minus 12 would equal 0. X plus 12 would equal 0. And then, likewise, x would equal 12, and x would equal negative 12. And life is all good. As long as we have factorable quadratics, then we are very easily tested in this area to just factor and then solve each individual piece. But what happens when we run into a situation when we're given a quadratic that is not factorable, like this one? X squared minus 20x plus 32 is equal to 0. Now in this case, I can't think of any two numbers that multiply to 32 and add to 20 at the same time. And so when we run into a situation like this, we're going to use a method known as completing the square. And in fact, I'll go and type that in because that is the title of today's lesson. So in order to figure out how to do this problem here, this problem number 3, before I do that, I'm going to go ahead and just copy and paste him. And I'm going to put him on the side because I'm not going to worry about him right now. In fact, before I do that, I'm going to delete these two guys, and we're going to go through a quick little exercise. I'll go and paste him here. We will come back to him. Don't worry. We're not going to leave this guy abandoned. We're going to come back and finish this up. But completing the square, the nature of the technique, comes from the idea of understanding perfect square trinomials. So let's review a perfect square trinomial real quick. A perfect square trinomial is something that looks like this: x squared plus 10x plus 25. And this thing is factorable. It will factor into x plus 5 and x plus 5, which can then be consolidated into x plus 5 squared because they are the exact same thing. Slightly below it, I'll do another example here. I'll do x squared minus 6x plus 9. And that's going to be factorable into x minus 3 times x minus 3, which can be consolidated into x minus 3 squared. So I'll let you try one on your own if you want. I would encourage you to pause this one. So I'll give you two to do here. So x squared minus 18x plus 81. And then x squared minus 12x, let's make it plus 12x plus, and if you can think of the number I'm going to put down, you might as well just say it because you'll be ahead of the game. It is actually 36. Very good. So take a second and pause, and then join us when you're ready to rock and roll. At this point, if you have paused and attempted the problem, you should get x minus 9 times x minus 9, or simply x minus 9 squared. And if you were to fast track this one, this would actually just be x plus 6 squared, but if you wanted to make sure he was expanded, it was all good. So the perfect square trinomial is a very special type of trinomial because it has a very peculiar kind of property. If you look at the inside terms, they all have the same thing in common. They're all kind of, similar in some way. This 10 can be made by 5 plus 5. This negative 6 can be made by negative 3 plus negative 3. The negative 18 is negative 9 plus negative 9. And then the negative 12, or rather the 12, is 6 plus 6. So notice the relationship here. We always have the same number happening. Always the same number happening. And they're being added together to get to the centerpiece. Well, not only do those two numbers add up to get to the center term, they also multiply to get the last term. So this is 5 times 5. This would be negative 3 times negative 3. This would be negative 9 times negative 9. And this would be 6 times 6. So from here, another way of looking at this is you could call him 5 squared. You could call him negative 3 squared. You could call him negative 9 squared. And you could call him 6 squared. So hopefully you have this in your notes. Hopefully you're establishing that relationship right now. And so another little tidbit on the relationship here is notice the relationship between the 10 and these numbers right here. 10 is double of 5, or 5 is half of 10. 5 is half of 10. Here, negative 6 is half of, or rather, sorry, not negative 6, what am I thinking? Negative 3. Negative 3 is half of negative 6. Negative 9 is half of negative 18, and so on and so forth. So, how does this review of the perfect square trinomial help me with what we're doing today? Well, remember, today we're doing something called completing the square. So, completing the square requires us, and I'll go and get this in our notes also, completing the square is a technique used. Completing the square is a technique used to solve a non-factorable. Now actually it can be used for a factorable quadratic, but honestly if the quadratic is factorable, I think it makes sense to just factor it. So completing the square is generally used to solve for a non-factorable quadratic expression or quadratic equation. And it is done by creating a perfect square trinomial, just like the ones that we did a few seconds ago. Now there are other uses for completing the square that we're going to cover later on in the class, but right now the only thing you need to be concerned about is we will use completing the square to solve for a non-factorable quadratic equation. So, how do I do a non-factorable quadratic equation? Well, first off, I'm going to change colors. I'm going to switch back to yellow and say x squared minus 20x plus 32 is equal to 0. Well, what I'm going to do is I'm going to go and subtract 32 from both sides. And I'm going to get x squared minus 20x. I'm going to leave myself a gap right there. I'm going to leave myself space. And that's going to be equal to negative 32. Now, I'm going to go back. I'm going to go and remind us of x squared minus 10x plus 25, an example we did before, or this was plus. What I'm going to do is I'm going to say that this was 5 plus 5. Right? We saw that a few minutes ago, right? Now, I established a relationship that 5 was half of 10, and that we took that 5 and we squared it to get the last term. So, what I'm trying to get you to see here is that this 20 is going to be my key to completing the square. What I'm going to do is I'm going to go and add the box on this side. Now, when it comes to integrated math, in order to keep equations equal to each other, whenever I add something on one side, I have to add that exact same thing on the other side. So this balances the equation out. So I added a box on one side, I have to add a box on the other side of that equal sign to keep things equal. The question is, what goes inside the box? Well, remember, the 5 squared is what got me to the 25. 5 happens to be half of 10 also. So I'm going to throw in half of the middle term into this box. So what is half of negative 20? Well, that's negative 10, and I'm going to square that. What I do to one side, I have to do to the other, so negative 10 again gets squared. And what I'm going to do is I'm actually going to simplify this out. I'm going to get x squared minus 20x plus negative 10 entirely squared will be 100. And that's going to equal, this is going to become 100 also. And then 100 plus negative 32 is positive 68. And then from here, this is factorable. It can factor into x minus 10 and x minus 10, consolidating itself into x minus 10 all squared, equaling 68 from before. And now from here, I'm going to go ahead and undo this square at the top. And the way I undo a square is I square root both sides. And I get x minus 10 is equal to, now remember, I took the square root of an x in the middle of an equation. So this is not going to be rad 68. It's going to be plus or minus rad 68. And so from here, I'm going to get x equaling, how do I get x by itself? I'm going to add 10 to both sides, and I'm going to say 10 plus or minus rad 68. Now from here, the rad 68 is not totally done yet, because if I'm correct, I believe this thing can be simplified down into 4 and 17. Now let me just double check and make sure that's correct. 17 and 4, 8, 2, 68. Yes, that does in fact equal. So I have to simplify that radical since I can. And then this becomes, the 4 becomes a 2, so 2 rad 17 plus or minus, and then the 10 comes along for the ride, and you have x equaling that. So that is how you solve a quadratic that can't be factored using completing the square. Let me do another example real quick, and then we will get back to this. I know it's a long process, but after a while it becomes easy. Alright everybody, we are back with the next example here. So here we have x squared plus 22x equals negative 80. Now from here, if you want to, you can try to factor it. You can say x squared plus 22x plus 80 is equal to 0. But good luck trying to find those numbers. I really can't think of anything that would allow that to happen, so he is definitely not factorable. So that leaves me with option 2, which is completing the square. So I'm going to go ahead and do x squared plus 22x. I'm going to leave myself some space there, equaling negative 80. And now, again, just like last time, I'm going to add the box. And I'm going to square the box. Now, again, what I do to one side, I have to do to the other side. So if I added a box squared to the left, I have to add a box squared to the right. Now, what number goes inside the box? Well, remember, in every situation we've seen with a perfect square trinomial, this number that goes inside is always 1/2 the middle term. So you have to look to your middle term, which is 22, and chop that thing in half. So you get 11. And then 11 would go in here. Again, I'm just keeping the left and right sides balanced. So remember, I'm making these balanced by adding the exact same thing, and therefore I'm not changing anything to the equation. So on the left side, I'm going to get x squared plus 22x plus 121 is equal to negative 80 plus 121. Now, this is probably the last time I'm ever going to do the equation like this. In fact, I'm going to do this problem again, just to show you guys a shortcut for completing the square that I think is going to help you move a little bit faster. And so from here, this guy's going to become 41 once we add those guys up. This will become x plus 11 and x plus 11, 11, and that consolidates into x plus 11 squared, equaling 41. To get the x by itself, I'm going to go and square root both sides. Square root of 41, goodbye. And then I end up with x plus 11 equaling plus or minus root 41. And again, I'm going to go and just subtract 11 from both sides. I'm just getting x by itself. There's nothing magical about it here. So I'm just going to go ahead and go negative 11 plus or minus rad 41. Now, it's important to note that this is negative 11 plus rad 41 and negative 11 minus rad 41. And I didn't do that in the last example, but in the beginning, I'd like you guys to do that. Separate your answers. That way you guys can be absolutely clear. You're getting two answers for your quadratic. So let me show you the shortcut real quick. This one here, I'm going to do everything exactly the same. I'm going to say x squared plus 22x plus the box equals negative 80 plus the box. Now, it's a shortcut that was shown a while ago, and I always do completing the square this way, and you guys will probably also do completing the square this way, because you'll see me do it all the time. What I do is, instead of doing this move here, and then this move here, what I do is I just bypass all of that and throw down one full parentheses being squared. Now, if you notice, the number that's inside the box, this number 11, is the same number that's inside the parentheses when it's being squared. So what I do is I literally just pull one 11 from the box, and I pull one x from the x squared, and I pay attention to that sign right there, making it 11. And it just shortcuts it. And that gets me negative 80 plus 121, which we already solved for. So I'm going to be doing the shortcut method more often, so just make sure you guys are staying aware of that. Let me do another example. Alright, and here comes the next example using the shortcut. Obviously not factorable. Can't have two numbers that multiply to 17 and add to 10 at the same time, so I will go ahead and subtract 17 from either side. And I will get x squared plus 10x. I'm going to leave myself some space. That's going to equal negative 17. And then what am I going to do? I'm going to add the box. And on the right side, I'm going to add the box. Again, because I add the boxes on either side so I can keep the equation balanced. Take a second and think what number goes inside the box. It will be half the middle term. Half of 10 is 5. Now here comes the shortcut. I'm going to draw one set of parentheses being squared, and that's going to draw an x plus a 5. Remember, one x here, one 5 here. Now, I know what some of you are thinking. Wait a second, what happened to the 10? Where did he go? Well, remember, what is x plus 5 squared? Well, that's x plus 5 times x plus 5. And if I multiply that out, I get x squared plus 5x plus 5x plus 25, in which case, there's your 10x that disappeared on you. So it's in there, it's just not foiled out yet. So from here, the shortcut, I think, is pretty fast, and I like it, so I will continue to use it. So this is going to be negative 17 plus 25, so that looks like it's going to get me, looks like 8. Square root on either side. I get x plus 5 is equal to, looks like plus or minus root 8, and I know he can be simplified, I'll do that in a second. Minus 5 from either side to get x by itself, so x equals negative 5 plus or minus root 8. When I split my answer, I will then simplify my radical. Rad 8 on the side here is a combination of 4 and 2 underneath the radicals. So that guy's going to go away to become 2 rad 2. So what I get is 5 plus 2 rad 2 and negative 5 minus 2 rad 2. And there are your answers for this problem. Now from here, I know what some of you are also thinking. So these problems have been pretty easy because the middle term has always been even and easy to chop in half. Well, what happens if we throw down an odd number? Does that impact our answer? Well, of course it does. If I give to you an example 4 here, and I'll go and switch back to yellow, x squared minus 7x plus 4 is equal to 0. Well, we've got an odd number going on up in here, so we'll do completing the square as we always do. So we're going to subtract 4 from either side. Now this is where the shortcut is really helpful when it comes to these odd numbers here. So x squared minus 7x is equal to negative 4. Again, I left myself some space, and the reason why I left myself some space is because I'm going to add the box. Now, if you're wondering why I drew the box like that, that's actually a pretty good question. Now, I drew the box like that because it's actually going to be a fraction inside the box. Now, inside the box is half of the middle term. Well, how do we get half of the middle term here? We literally take the number negative 7 and we divide it by 2. I must caution you, please don't use decimals here. Squaring decimals is really, really difficult. Squaring fractions, on the other hand, is really, really easy. So from here, the negative 7 over 2 will come onto this side. Now, you see why the shortcut is so helpful. It's because once you throw down your squares, you just pick one x and one box, and you just slap down an x minus 7 over 2 all squared. And that's going to equal, well, this is going to be a little bit harder, so I'm going to do them on the side here. So negative 4 over 1 plus 7 squared is 49, 2 squared is 4. So I'm going to need to have a common denominator if I'm going to simplify this fraction here. So I'm going to get negative 16 over 4 plus 49 over 4. Again, what am I doing? I am trying to simplify this portion of the problem right here. I'm trying to simplify them into one number. So that's going to get me 33 over 4 once I add these two guys up. So what do? I do exactly what I've been doing this whole time. I take the square roots of either side, and I get x minus 7 over 2 is equal to plus or minus the square root of 33 over 4. Now this is a little less complicated actually than you would think. The square root covers the whole thing, but what we can say, little exponent rule here, the square root of 33 over 4 is the same thing as the square root of 33 over the square root of 4. And I do that because one of these things I can actually figure out. The square root of 33 I cannot, but the square root of 4 is 2. So let me bring him down again. So x minus 7 halves is equal to plus or minus only root 33 up top now over 2. Now you see how advantageous that is. Now I've got a common denominator that I don't need to look for anymore. So I'm just going to add 7 over 2 to either side. So I get x equaling 7 over 2 plus or minus root 33 over 2. Now when I go to split this up, I'm going to split up the answers into plus and minus, but I'm also going to combine my answers into one denominator. So what it's going to look like is this. 7 plus rad 33 all over 2, or 7 minus rad 33 all over 2. And both of these are your answers here. Okay, let's go ahead and do another example that's a little more difficult. Okay, everybody, let's take a look at this example, and this is the worst that it's ever going to get. Now, actually, when it comes to solving a quadratic equation like this, I would not even use completing the square on this one. But because I want to show you what it looks like, and because I think this is so nasty that you'll gain an appreciation for the technique we will use in a later chapter, and when I say later, I mean the next one, you will see how it goes. And so a couple of tidbits about completing the square that are to be learned in this one, so just make sure you're paying attention. The shortcut is going to be pretty helpful in this one. I'm going to go ahead and subtract 2 from either side, and I'm going to have 3x squared plus 5x, and I'm going to leave myself space just like last time, and it's going to equal 24, 26 minus 2. Now, there is a rule in completing the square, and the rule goes like this. In order for completing the square to be possible, the leading coefficient of in front of x squared, that's what that caret top means, it means x raised to the second power, must equal 1. It has to equal 1 in order for this thing to work. Right now we're in trouble because our leading coefficient in front of x squared is 3. It's not 1. Okay? So how do I deal with such a problem? Well, what I'm going to do is I'm going to go ahead and factor out a 3 on GCF. Now, I know what you're thinking. Wait, but there is no GCF here. 3, 5, it doesn't work. It does. Let me show you why. Because what I'm going to get here is I'm going to get x squared here. Plus, what happens if I remove a 3? Well, remember, factoring is division, right? So I'm going to go and factor out the 3 by dividing the 3. Well, that just becomes 5/3 x. And I'm going to go and leave myself the space, and that's going to equal 24. Now again, this one is a really nasty problem, so you're not going to like it, and I'm sorry, but it definitely is something I want you to keep in your back pocket here. From here, I'm going to do exactly what I've always done. I'm going to add the box. Now the box is going to be rectangular because I'm going to end up with a fraction. I think you can probably already tell that. From here, I'm going to add the box again on the other side. Now this time, the box on the outside needs to get a little bit of a special treatment. And that is, that box needs to get multiplied by 3. Now, I'm sure you're wondering why it gets multiplied by 3. Well, it gets multiplied by 3 in order to keep balance to the equation. Because if you look at this box right here, he is being multiplied by a 3. Which means this box needs to get multiplied by a 3 also to maintain its weight in the problem. So the number that goes inside the box will be half of the middle term. Well, what's half of 5 over 3? Well, 5 over 3, half of it is being like being multiplied by 1/2, so that's going to be 5 over 6. And I know it's getting ugly, but I'm going to keep on moving through this problem here. So you see why the shortcut plays such an easy role, because you have 3, and then from here you can just say x plus 5/6 all squared. And that's going to equal the right side. Now the right side is going to be pretty complicated. That's going to be, the 5 over 6 squared is going to be 25 over 36 times 3. Now, these two pieces can cancel each other out, kind of, giving me 25 over 12. But remember, this 24 is being added to that, so it's 24 over 1 plus that. So from here, I'm going to have to find a common denominator in order to figure out what this is. So the common denominator is going to be 288 over 12 plus 25 over 12, which will then get me 313 over 12. And now from here, I'm going to divide by the 3 to get rid of the 3 here. And then, dividing by 3 is like multiplying by 1/3. So, whoops, I'm going to clean that up a little bit right here. And then I get x plus 5 over 6 squared is equal to 313 over 36. So it's all downhill from here. I'm going to square root both sides. I'm going to get x plus 5/6 is equal to plus or minus. Again, I'm going to square root these two pieces individually, so I get the square root of 313 over the square root of 36 is 6. Common denominator happens organically. It should. And then I end up with x equaling negative 5/6 plus or minus the square root of 313 over 6. And if you wanted to combine those answers, you could say negative 5 plus rad 313 over 6, or negative 5 minus rad 313 over 6. And that will close up that problem. Now again, I know that was a pretty painful process. Again, I probably would not use completing the square on that problem, but I also need to show you guys how to deal with completing the square when you have a leading coefficient that is not 1, because that will be part of your reality when we go to graphing quadratics using completing the square. So something for you guys to get used to. For now, I think that will be enough to close up shop on completing the square, and we will have some practice problems in class. See you later.